to the Nernst equation. So how many moles of electrons are involved in this? 2. Sometimes it's not so obvious, so this can trick people. So make sure that you pay attention to this. This one is a pretty obvious one. All right, now we have everything that we can put in. We calculated, or you calculated, the standard potential for the cell. You calculated Q, and you told me how many moles of electrons there are. So we can go and put this in. So we calculated positive 1.03 volts minus the gas constant times the temperature. It was at room temperature. Natural log of Q. We had 2 moles of electrons and Faraday's constant here. And now if we do the math, we this whole term comes out to 0.0592 volts, and we get our answer, which is a positive number there. So just a note about units and constants. Where did volts come from here? Well, the moles canceled out, and the Kelvin canceled out, and we were left with joules per coulomb. And conveniently for us, joules per coulomb is a volt. So all our units add up here. And just a note about significant figures in doing these problems. The Nernst equation, boy, significant figure fun. If you want to make sure you know significant figures, here you go. Significant figure rules for logs. We have significant figure rules for multiplication and division. And then significant figure rules for subtraction. So one equation gives you every type of significant figure rule. So that can be a lot of fun as well. All right, but I'm going to try to make it easier for you on an exam and avoid some math mistakes. All the problems I'm going to give you are at room temperature. And so the gas constant is a constant. Temperature for these problems is going to be a constant, always room temperature. Faraday's constant is a constant. So all of these I'm going to give you the value that they all add up to. And if you use log instead of natural log, there's this value as well. So these will be given to you on an exam. So you'll see these equations on the exam as well, and you can use them. So this is for natural log, this is for log. So we are not going to test your ability to multiply room temperature times the gas constant divided by Faraday's constant. So that's going to make it a little easier in doing these problems. All right, so what about at equilibrium? What does Q equal at equilibrium? So Q equals K at equilibrium. What does delta G equal at equilibrium? 0. And so that means that we knew before from this equation, when this is equal to 0, then delta G naught equals minus RT, natural log of K. So Q equals K at equilibrium. And so we had this equation that we used before. We now have this equation. So here it related delta G naught to the equilibrium constant. Here we relate delta G naught to delta E naught. And so I think you can see what's coming. We're going to relate these two together and come up with an expression where you can calculate equilibrium constants from standard reduction potentials. So you may be asked to do this as well. So everything in these units are, in fact, related to each other. And the only thing we have left today is answer this question about how B12 is reduced in the body. So you're just going to have to wait to find out. Don't worry, you won't get heart disease between now and Friday. And I'll let you know how it all works out on Friday.